this lesson, you'll learn to graph inverse variations and solve problems involving inverse variation. How is inverse variation related to the gears on a bicycle? The number of revolutions of the pedals made when riding a bicycle at a constant speed varies inversely as the gear ratio of the bicycle. In other words, as the gear ratio decreases, the revolutions per minute, RPM, increase. This is why, when pedaling up a hill, shifting to a lower gear allows you to pedal with less difficulty. Recall that some situations in which y increases as x increases are direct variations. If y varies directly as x, we can represent this relationship with an equation in the form y equals kx, where k does not equal 0. However, in the application above, as one variable increases, the other value decreases. When the product of two values remains constant, the relationship forms an inverse variation. We say that y varies inversely as x, or y is inversely proportional to x. Y varies inversely as x if there is some non-zero constant k such that either in your Algebra 1 book it has just the first form, ky or xy equals k. I prefer the second one because it looks more like what we already had for direct variation. So with direct variation it was y equals kx, so for inverse variation it's y equals k divided by x. The owner of Superfast Computer Company has calculated that the time t in hours it takes to build a particular model of a computer varies inversely with the number of people, p, working on the computer. The equation pt equals 12 can be used to represent the people building a computer. Complete the table and draw the graph of the relation. Okay, the number of people is the independent variable, so this time is going to be the dependent variable. So I'm going to divide both sides by p, so my equation is going to be t equals 12 divided by p. 12 divided by 2 is 6, 12 divided by 4 is 3, 12 divided by 6 is 2. Now I want to start using a calculator because it doesn't come out quite as nice, but it's not that bad. 12 divided by 8 is 1.5, 12 divided by 10 is 1.2, and 12 divided by 12 is 1. Notice when we go to plot our points, we're only going to have values in the first quadrant. Our first value p was 2, 6, 3, 4, 6, 2, 8, 1.5, 10, 1.2, 12, 1. As the number of people, p, increases, the time it takes to build a computer decreases. Graph an inverse variation in which y varies inversely as x and y equals 1 when x equals 4. So to find k, my constant variation, we're going to multiply both sides by 4, and I have 4 equals k. So my equation is y equals 4 over x. 4 divided by negative 4 would be negative 1. 4 divided by negative 2 is negative 2. 4 divided by negative 1 is negative 4. Oh, 4 divided by 0, we can't do that. That's undefined. 4 divided by 1 is 4. 4 divided by 2 is 2. And 4 divided by 4 is 1. In the first example, we were working with a real-world situation with people and time, which neither one could be negative. But this is just a theoretical graph, so sure, we can have positives and negatives, plot our points, and connect them with a nice smooth curve that continues forever in both directions. The term doesn't come up in this book, but the x-axis is going to be a horizontal asymptote, and the y-axis will act as a vertical asymptote. Asymptotes are lines that our graph approaches. If x sub 1, y sub 1, and x sub 1, x sub 2, y sub 2 are solutions of an inverse variation, then x sub 1, y sub 1 equals k, and x sub 2, y sub 2 also equals k. So by substitution, they must be equal to each other. The equation x sub 1, y sub 1 equals x sub 2, y sub 2 is called the product rule for inverse variations. You can use this equation to form a proportion So they divided both sides by x sub 2, y sub 1, and they have x sub 1 over x sub 2 equals y sub 2 over y sub 1. You can use the product rule or proportion to solve inverse variation problems as well. Now the proportion for direct variation, we had 1, 2, 1, 2. So in an inverse variation situation, we've got 1, 2, and 2, 1. So it's reversed, which makes sense. It's an inverse. If y varies inversely as x and y equals 5 when x equals 12, find x when y equals 15. I'm going to do this one using both methods so you can compare and decide which one you like better. First, we're going to use the first equation we had, so substituting in y equals k over 12. So we'd multiply both sides by 12, and we get 60 equals k. So our equation is going to be y equals 60 over x. And they ask us to find x when y equals 15. So we're going to substitute 15 in for y, multiply both sides by x, and then divide both sides by 15, so x equals 4. Using the other method, my x sub 1 is 12, my y sub 2, is 15. My x sub 2 is what I'm looking for, and my y sub 1 was 5. Cross products, and I've got 60 equals 15x. Divide both sides by 15, and voila, we have x equals 4. The advantage is, obviously, if you're just solving for one value, this is going to be pretty quick as long as you can remember where your numbers go. I think I'm going to favor the first method because it's similar to how we did direct variation earlier in the same textbook. So I'm going to substitute in y is 8, I'm looking for k, when x is 6, so I'm going to multiply both sides by 6, and I get k equals 48. Now I can substitute in y equals 48 over x. My k value is 48, and I want to find y when x is 4, so y equals 12. When two objects are balanced on a lever, their distances from the fulcrum are inversely proportional to their weights. How far should a 2 kilogram weight be placed from the fulcrum if a 6 kilogram weight is 3.2 meters from the fulcrum? A lever is a bar with a pivot point called the fulcrum. For a lever to be balanced, the lesser weight must be positioned further from the fulcrum. I'm going to let the 6 kilogram weight be my x1 and the 3.2 meter distance be my y1. So I've got 3.2 equals k over 6. When I multiply that out, I got k equals 19.2. Now that I've got my magic number here, y equals 19.2 over x, I'm going to substitute 2 in for x. So y equals 19.2 divided by 2, which gives me 9.6, and my units were meters. The product rule for inverse variation states that if x sub 1, y sub 1, and x sub 2, y sub 2 are solutions of inverse variation, then we can use the proportion x sub 1, x sub 2 over y sub 2, y sub 1 to solve problems involving inverse variation. Or I preferred the form y equals k over x because it was more similar to the y equals kx that we used for direct variation earlier in the same textbook.